Okay, we'll give everyone a few more minutes because I was late logging in. I always try to be 5 minutes early, but I had to restart my computer about 3 times. The plan for today is we'll spend about an hour going over direct shear testing. So I'll give you sort of a condensed version of the PowerPoint slides associated with direct shear. We'll go over an example problem with direct shear results using clay and direct shear results using sand. Then we'll take a break. And then we'll discuss more circles and triaxial testing. And then we'll discuss UU testing, and we'll also discuss CU testing. And I'll go over an example problem or two associated with each of the different testing methodologies. And then at the end of the class, I'll open the unconfined compressive strength quiz for students to review. So they'll have an opportunity, or you'll have an opportunity to review any mistakes that you may have made on the quiz. If you didn't have any mistakes on the quiz, you won't really have anything to review, so you don't need to stick around. Before we get started, I was thinking next week as well, we can maybe have another couple-hour session where I can open your direct shear quiz, and then I can also be available for questions as students are working through the review assignment and prior to the test. Would you guys be amenable to that? Working around your schedule, so I didn't know if Wednesday afternoon would work for you guys. I'm available Monday afternoon, Wednesdays, and Thursday afternoons. Whatever works better for you guys. Anyone have an opinion? Wednesday sounds good. Okay. I'll open up the quiz on Wednesday afternoon at 1. I'll send an email about it. And there's also a review assignment associated with next week's test that's posted on Learn. And I'll be available to answer questions on that review assignment or any questions that students have on the material for next week's test. I'll also send a very detailed email next week regarding this week regarding next week's test, and we'll talk more about it at the end of class today. Before we get started on this week's material, was there any questions from last week's material? No. The first 4 weeks in this course are the busiest, and after that, I think the workload lightens up. So I think you'll find the workload eases up, so the pace of the course will be a little more enjoyable. Yeah, I figured if I made it busier in the first 4 weeks, then the last 8, when you're busy with ARP and your other courses, then this one won't take up as much of your time. Okay, I'm hoping everybody can see this. I'll put my chat on the other screen. Okay, direct shear testing. Why do we do direct shear testing? Well, we do direct shear testing so we can determine our shear strength parameters for either a clay or a sand material. So that's the purpose of a direct shear test. With a direct shear test, we shear soil along a failure plane that's determined by the shape of the shear box. So the shear plane is in between the top and the bottom half of the shear box. And to obtain the results from a direct shear test, we actually have to do 3 tests so that we can plot them and generate our Moore Coulomb failure envelope from that. This is just a schematic of what we discussed last week with respect to shear and normal stresses. So your normal stress acts perpendicular to your failure plane. And to calculate your normal stress, you would take your normal force and divide it by your shear area. Whereas a shear stress will act will act parallel to your shear plane. And to calculate your shear stress, you use your shear force and you divide it by your shear area. Okay. This is just a schematic of what your direct shear apparatus would look like. With direct shear testing, can everyone see I have two little notepads. They're kind of fluffy. One's pink, one's black. Hopefully you guys can see it. I tried to do this so you could see the difference. So imagine this pink fluffy notepad is the top half of your shear box, and the black fluffy notepad is the bottom half of your shear box. So with a direct shear test, you're applying a shear force to to your shear box. And on one side on the top half of your shear box, you sort of have an arm. And so what this arm is doing is it's holding the top half of the shear box stationary. So the top half of your shear box, so this pink fluffy notepad, isn't able to move when you're applying a shear force to the shear box. So you have this arm that holds it in place, and you will have a load cell that's attached to that arm. And this load cell is measuring what is the shear force that's required to hold the top half of this box stationary. Meanwhile, while the top half of this box being held stationary by the arm, the bottom half of your shear box is able to move. So initially, you'll see that the top and bottom half are lined up parallel or perpendicular to each other. So they're one on top of the other. But as you're applying a force, say to the left-hand side of my shear box, the top half is remaining stationary, but the bottom half is not. The bottom half is moving because there's not an arm holding it in place. So you'll see that the contact area between the top and the bottom half of the shear box is reducing because they're no longer aligned perfectly with one another and stacked perfectly on top of one another. You'll see that with this schematic here, now you have a bit of an offset. And so this offset distance is measured by your linear displacement sensor. So this bottom half of the shear box is moving while the top half of the shear box is remaining stationary. So this is sort of the premise of a direct shear test. So when you're doing your direct shear test, you measure the shear force required to hold the top box stationary, and then you measure this offset distance here with a linear displacement sensor, so you can determine what is the displacement or the change in the length associated with the bottom half of the shear box. So this slide here is just a schematic of that, and then it's just indicating how you would calculate your normal stress and your shear stress. So when you're doing your shear stress as well, your direct shear test, you have a normal force that's applied to your specimen, and also that to you in a couple slides. And that normal force that's being applied is weight that is added to the lever arm of your direct shear testing apparatus. As I mentioned, you have to do 3 tests or at least 3 tests so you can generate your Mohr Coulomb failure envelope. So in our lab, we apply 3 different weights to the lever arm. So we use 8 kilograms, 16 kilograms, and 24 kilograms. So you have to run this test 3 times with each of those different normal forces, and then you calculate the shear force required, or the shear force, the maximum shear force before you experience shearing or displacement. This is just a schematic of the direct shear machine. You'll see right here. This is the lever arm right here, and you'll see that there's a bit of a circular contraction at the base of the lever arm, and this is where you apply your weights. So these weights is where you apply the 16, the 8, and the 24 kilograms to your direct shear apparatus. In our lab, we generally only do direct shear testing on granular material, and that's because it can be done really quickly. I'll talk about direct shear testing on clay in about half an hour. We do granular material because it can be done quite quickly. You can run a test in about 15 minutes. The shear box is shown on the right-hand side of the PowerPoint slide, and generally the shear box is about 60 millimeters long by 60 millimeters wide, and it ranges between 25 and 30 millimeters in height. We use something, so when we're doing the direct shear test, we actually need to separate the top and the bottom half of the shear box so that we don't have any friction between the steel components when we're conducting the test. So we use something called separation pins, and we use those so that we can create that 1 millimeter gap so we don't have the friction between the steel when we're conducting the test. And if anyone has any questions, you can unmute yourself or just ask the questions in the chat. So this is just a bit of general information on the direct shear testing in sand, and this information only applies to direct shear testing in sand. We would have different shearing rates, and we would have different requirements for in clay. So as I mentioned, you should develop a shear plane in about 10 to 15 minutes when you're conducting your direct shear test in sand. And we use a strain rate or a displacement rate of 1 millimeter a minute when we're conducting the test in sandy material. I've gone over the rest. So we continue with the test until our shear force starts to decrease in value. So you can see it on a graph. We plot it while we're conducting the test. You'll see that your shear force measurement starts at 0, and then it eventually peaks, and then it starts to drop off. So the moment that your shear force starts to drop off, we'll run the test for about 0.5 millimeters more of displacement after that. But what we're trying to obtain is that maximum shear force value. Generally in the sand, we don't see 6 millimeters of displacement. We generally see that we have a maximum shear force, and then our shear force drops off after the shearing has occurred. And as I mentioned, we do have to run 3 tests. Yes, it does say that. And it depends on what type of sand you're using, Pavel. So it depends on the coarseness of the sand. We have it, so the sand that we're using in the lab, we can use 1 millimeter a minute.
Question.
Sure.
So for the normal stress and shear stress equations, that A value, like what exactly is that? Is that the area of contact prior to failure or after?
No. So when you're doing when you're calculating your shear and normal stresses, I think that was Timothy, right? Was it Timothy that asked the question? So
yeah,
it's your contact area at that moment in time. So initially your contact area is just your length times your width of your shear box. But as the test progresses and you develop different shear forces are required to hold that top box stationary, your area becomes your corrected area. So your area is your width times your length minus your displacement value. Because if you see this black fluffy notepad, you'll see that there's a bit of an offset now, right? So your contact area isn't the full width of these notepads or of your direct shear box. You now have an offset. So your contact area is now decreased, right? So if you can see that here, your contact area is now from here to here. It's not the full length anymore. So your area is your corrected area, so that you have to take into account that offset that's occurred because the top half has remained stationary and the bottom half has moved. Does that make sense, Timothy?
So we're talking about a contact area at a specific moment in time during the test.
Correct.
Okay.
So when you do your analysis, and we'll get into this, of direct shear results, you always take your maximum shear force. So your maximum shear force, if you were to convert that to a shear stress, you take the contact at that one moment in time. So we measure, when we're doing the test, we measure our shear force and our displacement every 5 seconds. So you would need to calculate your corrected area at each of those 5-second intervals. So your corrected area always varies because it's at a specific moment in time. Does that make it clearer?
Yeah, I think so.
Okay. Anyone else jump in? I'm happy to answer any questions. So as I mentioned, you have to run 3 tests. So you have to, once you run one test, so say you run a test using an 8 kilogram normal load or an 8 kilogram normal load, you would run your test. Then you would have to go and empty your shear box and put a whole new specimen in your shear box and then conduct the test again, say at a 16 kilogram normal force. You would go through until the shearing process is complete. Then you would have to remove that specimen and then put a new specimen in the shear box and run the test again at 24 kilogram normal force. So with a direct shear test, your normal force is always constant. So when you're calculating your normal force, it's determined by the mass of the weight that's applied to the top of the specimen. So you can't actually physically apply the weight to the top of the specimen. You're putting the actual weight on the lever arm portion of the direct shear apparatus. And then there's kind of an arm that comes up and over, and then that force or that load's applied to the top of the specimen. So to convert from kilograms to a Newton force, you're multiplying by 9.81. Our direct shear testing apparatuses at Red River College have a 10-to-1 lever arm. Yeah, so our lever arms on our direct shear testing apparatus have a 10-to-1 lever arm. And so what that means is that specimen feels a force that's 10 times greater than the amount of weight that was actually applied to that lever arm. So say, for example, I'm applying 8 kilograms to that lever arm. The force, or the normal force that that specimen actually feels, is 80 kilograms. And then I multiply my 80 kilograms by 9.81 to convert it to force in newtons. So that's why there was the 10-to-1 ratio, Pavel. That's just the ratio of our lever arm of our two direct shear testing apparatuses. Most do have a 10-to-1 lever arm, but there may be some that don't. The normal force is always constant. It doesn't matter what point in time you are at in the testing process, your normal force would be the same. Your normal force would always be the same. And when you calculate your normal stress would be your normal force divided by that corrected area that I previously talked about. Your shear force always varies with time. So your shear force is a measurement that's taken by the load cell, and that shear force is the force that's required to hold this top half of this box stationary. So the pink half, the top half of your box always remains stationary. So it's the force that's required by that arm to hold the top half of this box stationary. So that force always changes at every, like you're recording at 5-second intervals. So every 5 seconds, your shear force would be a different value. And that small, yes, you have to multiply the weight by 10 and then multiply it by gravity. And that's how you find what your normal force is throughout. So in any question, so anything associated with the lab, yes, you multiply by 10-to-1. When I'm doing it on a test, so on the test that you guys would write next week, I've already done the conversion with the lever arm, but I just want you guys to be aware of it for the lab. I don't do the conversions for the lab because that's part of doing the lab process, but on a test, I don't expect you to multiply it by 10. I've already done the conversion for you guys. That small delta value is the shear displacement. So hopefully there's no confusion. And I believe on the test, I'll double check this, I said don't multiply it by 10. So I think it's pretty clear on the test, but Pavel, I'll double check that. So that small delta is the shear displacement that's measured with your linear displacement sensor, and that's measuring the change in your contact area. So the change in contact area usually varies between 0 at the start of the test to, it can go up to about 5 millimeters. Again, this schematic here just shows you how your contact area changes as your top box is held stationary. Top half of your shear box is held stationary while the bottom half of your shear box moves. So again, your contact area decreases as the test progresses and the shearing process is in place. So to calculate your corrected area, as I mentioned previously, you use this formula right here. Corrected area AC is equal to your width, because you see here, if this is your width, so this is the width portion of your shear box, that's not changing. Your width is always the same. It doesn't matter if there's movement of the top or bottom half of the shear box, your width always changes. There's no change in the contact area for the width. If you look at the length, there is a change in the contact area for the length. So you'll see here, this is your new contact area for the length. From this point here to this point here is your new contact area of your two shear boxes. So the way you calculate that is, you know what the initial length of your shear box is, and that would always be provided to you in a test and on a quiz. You never have to know what the length of the width is. That will always be provided to you. And then the displacement or the change in contact between the top and bottom half of the shear boxes is this small portion right here. Hopefully this shows up. Oh, that didn't work so well. Is this, let me move that off, is this portion right here. And that portion is measured by your linear displacement sensor. So it's just the initial length of your shear box minus that displacement or that shear displacement measured by your LDS. So that's how you calculate your contact area. And so to calculate your shear stress or your normal stress at a moment in time, so at any time interval, your shear stress would simply be what your shear force is measured at that moment in time divided by your corrected area. And your corrected area is shown using that formula there. And then your normal stress is simply equal to your normal force divided by your corrected area. So we are generally taking, when we're doing our calculations, we're using the peak shear force. So your FS value that you're concerned with is your peak shear force, and you would calculate your corrected area at that time interval when your peak shear force was measured. And then normal stress, your normal force doesn't vary as the test progresses because you're still, the normal force is constant throughout the test. And then you would determine or calculate your corrected area at that point of failure. So where you have your maximum shear force. Does this make sense? I just want to make sure everyone understands. Okay. This is just an example of what direct shear results on sand look like. So if you were to run 3 tests and you were to plot them up and plot shear force versus displacement for 3 different normal loads or normal forces, this is what your data would look like. And then the table on the right is we've gone through and done the calculations, but I'll work through a couple examples with you on that. So for direct shear tests, what we like to do is we plot shear stress at failure versus normal stress at failure for the 3 individual tests that we're doing. So you'll see here that you can generate a linear line. No, it's only I'm only going to give you a rectangular one. No cylindrical surfaces on the test. Yeah, those are kind of funky equations. No. So anything I test you on the test is only related to the example problems that we've gone through. So if we haven't done an example problem on it, you're not going to be tested on it. Sometimes I just give you information in case you are exposed to it when you're working in industry, but if there's no example problem on it, you won't be tested on it. So this is just an example of some direct shear results. Again, with direct shear testing, we always plot our shear stress at failure versus our normal stress, and we generally have a minimum of 3 data points. You'll see that this is for sand material. So with sand material, you'll recall from our lecture last week, what is the cohesion for a sand material? Anyone recall? What's cohesion for sand? Can sand stand vertically unsupported? Right, 0. So your line of best fit always goes through the data point 0, 0 for a sand material. And then how do we determine our friction angle? We talked about this last week. How do we determine our friction angle using a Moore Coulomb failure envelope? Right, arc-tan. So you take your inverse tan of the slope of the line, and then you're able to calculate what your friction angle is for your direct shear test. Perfect, you guys are experts. Are you guys okay if I go through an example problem? I was going to go through one in sand and one in clay. You guys okay with that? Okay, perfect. I'm gonna stop sharing this screen. Okay, you guys can see this? My chat. Perfect. Okay. So this is example problem 4.2. So this is real data that we obtained when we ran a direct shear test on dry sand. So our shear box, we measured it to be 60 millimeters by 60 millimeters. So it's 60 millimeters in length and 60 millimeters in width. So you'll see with this data here, I plotted shear force versus displacement for this data here. So the information that we need to obtain from this plot is what is our maximum shear force. So you'll see on the plots here, I've identified what the maximum shear force is associated with each of the different tests. And you'll see there's a legend over here indicating that our normal forces were 490 newtons, 1470 newtons, and 2450 newtons. So the larger or the higher the normal force you have, the higher the shear force that should be recorded. So when you're looking at data, always make sure that that's what you're recording and you haven't mixed that up. So the next piece of information we need to obtain from this graph is what was our measured displacement at each of the maximum shear forces associated with each of the different normal forces. So I'll take a look at my plot here, and this is the 490 newtons normal force. I'll say, okay, well, the maximum shear force was 250 newtons, and the point in time that I obtained that maximum shear force was about here. So the displacement associated with that maximum shear force for test number 1 was about 2.5 millimeters. So then I'll go up to the next line on the graph, and I'll be like, okay, the maximum shear force was 924 newtons. That's recorded on here. And again, 924 newtons was documented to occur at about 2.5 mils of displacement. So I would record that as my displacement for the second direct shear test. And then I have one more direct shear test that was at 2450 newtons. So if I take a look, my maximum shear force occurred at about this data point right here. And I can just draw a vertical line down through the x-axis. And I noted that my shear displacement at that point was about 1.5 millimeters. So I'll go through how we do the calculations for each of the different data points. So you'll see here, I like to make these little tables, and I find these tables are informative, and I find it helps students organize their data. So what do you mean by everyone will have a slightly different answer? Just where you do the interpretation on the graph? Is that what you meant by that? Yes, exactly. So everyone will have a slightly different answer, and that's okay. I'm looking for the process. I accept a range. So say if you looked at the graph that has the maximum shear force of 250 newtons. If you told me the shear displacement at failure for that was 1.5 millimeters, well, I would be like, no, because that's not where the maximum shear force occurred. But if you told me it was about 2.4 meters, or if you told me it was 2.6 meters, sort of in that ballpark, it's open to interpretation. So there is sort of a range that I do accept. Is that okay with you guys? Does that make it? So yeah, so there's a range that's accepted. So that's why with questions where I ask you to do data analysis and interpretation on a test, I'm asking you to submit your solutions because I'm looking for the process and I mark the process. Obviously, I do mark the answer if it's correct or not, but I'm more marking the process and I accept a range of values. So that's what I'm looking for. So I do like when students make these tables. I find these tables help organize the data for the students. So the way I set up my table is I will have one column with my normal force, one column with my max shear force. I will have a column with my displacement at failure, and then I'll have a column for corrected area, and then I'll have a column for my normal stress and a column for my shear stress. So if I take a look at test number 1, I know my normal force is 490 newtons. That was documented on the table or on the graph here. I know my maximum shear force was 250 newtons. And I know my displacement at failure was 2.5 millimeters. So the first calculation I have to go through and do is my corrected area. So you were given the initial shear box dimensions, and they were 60 millimeters by 60 millimeters. So you know your width isn't going to change because your contact area width-wise doesn't change. So your width will remain constant at 60 mils. I always convert to meters because I find it easier to do the calculations and less chance of error if you just convert to meters. So the width of the shear box is 0.06 meters. And now I have to do my, I have to correct my length. So my initial length of the shear box or of my contact area was 60 mils or 0.06 meters. But now my contact area has been reduced because my top half has remained stationary and my bottom half has moved. And my contact area has been reduced by 2.5 millimeters. So I'm going to subtract 2.5 millimeters from my initial length of my specimen of 60 mils. So it's just 0.06 minus 0.0025. So to calculate the area, it's just length times width. And so my corrected area is 3.45 times 10 to the minus 3 meters squared. So I write that in my table down here. It's 3.45 times 10 to the minus 3 meters squared. And so to calculate my normal stress at failure, it's simply my normal force, which is shown on my graph of 490. So it's 490 here and 490 divided by my corrected area, which is 3.45 times 10 to the minus 3. So my normal stress at failure was 142 kPa. So I write that in my table here. My shear stress at failure is my maximum shear force divided by my corrected area. For this line on the graph here, or this test that was run, I know that my maximum shear force was 250 newtons. So it's 250 newtons divided by the corrected area, which is 3.45 times 10 to the minus 3. It's the same corrected area. And I know my shear stress is 72.5 kPa. So my next step is to plot this data point on the graph down here. So you'll see here, I know I already have one data point of 0, 0, and that's because this test was conducted on dry sand. So I know automatically I have a data point of 0, 0. And then I know I have a data point of 142 kPa and 72.5. So I'll just plot that here, 142 and 72.5 kPa. So it plots about here on the graph. So that's my first data point. If I was to go for test number 2, I would do the same process. So I would have 1,470 newtons. My max shear force was 924. My displacement, again, is 2.5. So luckily, my corrected area is the same. So my corrected area is still 3.45 because I measured the same shear displacement at failure. So I would just be calculating a new normal stress. So my normal force is 1470. So 426 kPa. And then my shear force would be 267.8 kPa. So I would just simply plot this on the graph here, 426 and 267.8, and I would have a data point there. I would go through the same process for my third graph. So I would use, my third line on my graph. So again, I know what my normal force is, and I know what my shear force is. I would calculate my corrected area and then calculate my shear stress and my normal stress. You find your, did I mess this up? Oh, okay. That's the next question. Yeah, so I always go through 0, 0 and do my line of best fit, Suraj. So anyways, yeah, so I do that, and then I plot up my third data point, which is approximately up here. I think I calculated it to be Kelly had it right, 470.9 and about 700. And so I just drew my line of best fit through 0, 0 and these 3 data points. And I got about 33.8-ish as the slope of my line, or I did the arctan of it. So I calculated my friction angle to be about 33.8. I'm going to flip over to, okay, you guys can see this. Yeah, so my normal stress was about 698 or 700 is close enough. And my shear stress, I got about 470. I think that's what Kelly got. Yes. So for test number 3, this would be your shear normal stress, and that's what you would plot on this graph here. And then you draw your line of best fit going through 0, 0 and calculate the slope of your line and take the inverse tan. And that's how you calculate what your friction angle would be for the sand material. On a test, you would need to indicate to me when I ask you to calculate the shear strength parameters for the sand material. There's 2 shear strength parameters you need to tell me about. The first one's the friction angle, which you calculate from the slope of the line. And the second one is cohesion. It may make sense to you that it should be 0 because it's a sand material, but you also need to identify that to me. So you need to identify to me on your graph or elsewhere that your cohesion value, so my cohesion is equal to 0 kPa. Any questions on how you do the direct shear analysis for a sand material?
So for finding the angle, you're just picking a point on your best fit line and using
Correct.
that as your inverse for your Reso run?
That is correct, yes. And so there's a range, like usually I take plus or minus 1 degree with respect to calculating your line of best fit. And that does actually give you quite a bit of leeway with determining your line of best fit. If you told me your friction angle was 25 degrees, or if you told me it was 40, well, something's incorrect, but plus or minus a degree is fine. Conrad, how do you find cohesion values of different materials? We're going to go through that when we talk about the clay or material that has cohesion. Sand, gravels, pure silts never have a cohesion value. They're always 0. But if you have a material with clay, it will have, or a silty clay, it will have cohesion. And I'll talk about how you determine that cohesion value. Any other questions on how you calculate your shear strength parameters for a sand material? Oh, what does friction angle imply? Friction angle represents the strength of your material, or it represents, imagine if you had sand that was being dumped by a dump truck. So the stronger a material is, the higher the shear, or the higher the friction value that it has. Friction angle also represents the natural angle that that material would stand if we just dumped it freely, say with a dump truck. So if we had sand and we had a dump truck that just dumped that sand and it was sort of cylindrical or cone shaped, it's the angle of repose, or the angle that that material would stand at without it being interfered with. So a higher value of friction angle means that it's a stronger material, Suraj. Okay, I'm gonna move on to this slide here. And I'll just spend a couple of minutes talking about direct shear tests on clay material, and then we'll go through an example, and then you guys can have a break. Testing or direct shear tests that are conducted on sand. Direct shear tests are always considered consolidated drain tests. And what this means is that when we're conducting the test, we're not generating any excess pore water pressure while we're conducting the test. So we're not doing our shearing at such a high rate that we're generating excess pore water pressure. And this will make more sense when we talk about the triaxial testing. If we think of sand, sand's quite porous. Sand has a high hydraulic conductivity. So it doesn't matter if the sand is wet or dry when we're conducting the test. That excess pore water pressure drains almost instantaneously. So we don't have to slow down the rate of our shearing process if the sand material is wet or dry, because it drains almost instantaneously. So our test duration is quite short. It's in the 10 to 15 minute range. Whereas if we think of a clay material, if we were to add additional weight to a clay material, well, clay material is not very porous. It doesn't have a high hydraulic conductivity. So when we add that additional weight, we generate a lot of additional pore water pressure. So when we generate that pore water pressure, when we're conducting the direct shear test in clay, we want time for that excess pore water pressure to dissipate. So when we do a direct shear test in clay, the shearing rate is really, really slow. So say, for example, in sand, we could obtain a data point in 15 minutes. Whereas if we do a direct shear test in clay, it takes us a week to 2 weeks to generate a single data point. So if we wanted to generate our Moore Coulomb failure envelope for a clay material when we're doing a direct shear test, it takes us anywhere from a month to 6 weeks to be able to generate that failure envelope. So instead of an hour and a bit, it takes us 6 weeks. So the shearing process in clay is much slower for a direct shear test in clay than it is for sand. So we do use direct shear testing in clay, so we can calculate something called our residual shear strength value. We use our residual shear strength value for slope stability analyses. So that's why it's important that we actually determine what this shear strength value is. So a residual shear strength value is the shear strength of a clay material after it's undergone significant displacement. So clays that are on riverbanks have undergone significant displacement, and they're at their residual shear strength values. Whereas if we looked at something that was offset from the river by 50 meters, 100 meters, those materials haven't undergone the same shearing process, so they're not at their residual shear strength parameters. So if we take a look at this plot here, there's two shear strength parameters we can determine for clay material when we're doing a direct shear test. These are your peak shear strength values and your residual shear strength values. So your peak shear strength values, we would use those if we're doing design work for an area that's significantly offset from a river bank, whereas we would use the residual shear strength parameters when we're doing design work along a riverbank, because I won't say all of, 95% of the outside banks of the Red River have undergone significant shearing, and the clay material that is adjacent to the riverbanks is at its residual shear strength value. When we do direct shear tests on clay material, we can determine the cohesion value. Cohesion values when clay materials are at its residual strength values, they're quite low. They're in the 2 to 5 kPa range, and they're slightly higher when they're at their peak shear strength values. So that's all I'm going to really say about conducting direct shear tests on clay. We don't do it in our lab because it's such a slow process. People may request it in industry, but it does take 6 weeks to generate enough data so that you can determine the shear strength parameters of a clay material. I'm going to go over an example problem of interpreting direct shear data with clay. And I think that's important because it helps you determine both what your friction angle is and what your cohesion value is. But before we start that, does anyone have any questions?
So why does it take so long? Because it takes a long time for the clay to be drained, or I didn't get that.
Yeah, so exactly, Tim. So when you're doing the shearing of clay material, you don't want to generate any excess pore water pressure. So the shearing process generates excess pore water pressure and the addition of the normal force. So you have to shear at such a slow rate that you're not going to be generating any excess pore water pressure during the shearing process. So instead of shearing at, say, 1 millimeter a minute, you're now shearing at 0.005 millimeters a minute. So when you start to shear, your pore water pressures go up. But in a sand material, it doesn't matter because it's so porous that water just drains instantaneously, right? But with a clay material, it can't because it has such a low permeability or conductivity. So with a clay material, you have to shear so slowly that you're not going to generate any excess pore water pressure during the shearing process.
Why is that excess pore water pressure so bad?
Excess pore water pressure reduces the shear strength of your material. So if you were to shear that clay so quickly that you didn't dissipate that excess pore water pressure, then your shear strength parameters are going to be exceptionally low.
Okay, I think it's starting to make sense now because I can't remember whether it was in this class or another one. You know, when there's water in the midst of soil particles, it tends to want to disperse them and move them apart, so there's less friction.
Exactly. So that was in this. That's in this course. So remember we talked about effective stress and total stress, and then pore water pressure. So when you have your total stress, it's the measure of the stress of the particle-to-particle interaction and the stress associated within the water itself or the water pressure, right? Whereas so the more water you have in that void space, it's trying to push those particles apart, and it's the particle-to-particle contact that increases the strength of the material. And the more those particles are pushed apart, the weaker your material becomes.
Okay, this makes sense.
So when you shear, if you were to shear at such a high rate that you're generating excess pressure or more water in that void space, you're pushing your particles apart. So the strength of that soil is significantly reduced. So if you were to do a direct shear test and then come back with results and have exceptionally low shear strength parameters, that means that your design is ultra conservative and it's going to cost somebody a lot of money. So they're not going to be very happy about that, right? So you want realistic values when you're providing them to the designer. Does that make sense?
Yeah, I think so.
Okay. I'm happy to answer questions after as well.
Hey, just another question.
Sure.
So in the real world, when you have a slope failure, does it happen very slowly at this rate, or would it happen more abruptly, like all of a sudden?
They happen slowly. They're almost always occurring, especially on outside bends. There's always some displacement because there's erosion at the toe or the water levels going up or down, but it's usually some event that precipitates the major like movement so that it becomes observable. So the two most common times of year when you'll see slope movement is associated with river levels going up and down. So if you're to have a flood event and your river level's high, actually the stability of your bank increases and there's no potential, I won't say there's no potential, but the potential for movement's minimized because you have hydrostatic forces acting on that bank, preventing the movement from occurring. But when the river levels drop, all of a sudden you have a saturated bank trying to push those soil particles apart. So the strength of your bank becomes reduced, and then you don't have that hydrostatic force anymore, and the bank weighs more, then the bank wants to move, right? So that's one common time, or the other common time is in the fall. And so I don't know if everyone's seen where the river level drops a lot in the fall, especially after they draw down at St. Andrews Lock and Dam. So that's another common time of the year when you'll see riverbanks move because the river level used to be higher and then all of a sudden it's lower and the banks are still saturated from when the river was higher. So Sean, I think it was Sean, they're always kind of moving, but there's events that precipitate larger amounts of movement. So if you look at outside bends between Emerson, or say the US border, and Lake Winnipeg, it's something like 95% of all outside bends have experienced at least one major slope movement, and likely multiple movement events or displacement events.
All right, thank you.
Does that answer your question?
Yeah, it answers it more or less. I think the water content of a slope is I guess it's really an event that causes it. Like even like on an overpass. You know, if it rains like crazy after it's been really dry for a period of time, I've noticed that is also a time that slope failure.
Exactly, right? Because you know what, the water can't infiltrate fast enough. So you probably get more shallow slope movements than you would deeper slope movements at that time period. But yeah, the water can't infiltrate fast enough into the clay material. So you would get some shallow slope movement. So water is usually not a friend to people in geotechnical, in the geotechnical field. We're usually trying to repel water in some sort of way, or reduce the amount of water that we have, because it's generally not our friend.
But we all have to drink it, so.
Yes, that's true.
Well, and I think a bit of moisture is good. You have to have that. I guess it's a range, right? You don't want your soil to be too dry, but you don't want it to be too wet. And so that's.
Yeah, exactly. Exactly. So like think of it in terms of constructability as well, right? When you guys do a proctor, you have an optimum moisture content, right? If you're trying to construct with material that's like to the right of your OMC, it becomes quite hard, right? And you have to use various techniques to dry out the soil, right? And if you're to the left of your OMC, it's also problematic because you can't get proper compaction, right?
Thanks for the answers.
Yeah, no problem, hopefully. Okay, I'm sure you guys are almost done. So we'll work our way through this example problem, and then we'll take a 10-minute break. Okay, so example problem 4.3 is a direct shear test on clay material. So instead of being on sand, it's on clay material. So what would we know for sure about this question when I say that it's on clay material instead of sand? Right, perfect. Cohesion's greater than 0. So this means that your line of best fit does not go through the data point 0, 0 on your graph. So if we look at this here, I've already given you your applied mass, and I've given you your shear displacement, and I've given you your residual shear force. So to convert from applied mass to a normal force, you just have to multiply by 9.81. So you'll see here, you just have to go 10 kilograms times 9.81, or 20 times 9.81, or 30 times 9.81. And from that, you're able to calculate your normal force. Your shear displacement for these specimens were recorded to be 7.1, 5.32, and 4.85. So that means that this is what the offset distance between the top and bottom half of the shear boxes was at your residual force. So, and then your residual force was measured with your load cell. And so your residual force was recorded to be 40, 62, and 98 newtons, respectively, for each of these 3 tests that were conducted. So similarly to a direct shear test that's conducted on sand, the width, it doesn't change. Your contact area width-wise remains unchanged. So if we're going to calculate what our corrected area is, the width remains unchanged. And so our length does not remain unchanged. Our length, or the length of our contact area, becomes smaller. So we know the length is 60 mils, so 0.06 meters. And if I'm looking at the first point, so if I'm looking at point 1 here, I'll label them 1, 2, and 3. Our shear displacement was 7.1 millimeters. So I just went minus 0.00710, which I've just converted 7.1 millimeters to meters. So I can calculate my corrected area to be 3.174 times 10 to the minus 3 meters squared. So if I want to calculate what my shear stress is equal to my residual shear force divided by my corrected area. I know my residual shear force is 40 newtons, and I know my corrected area is 3.17 times 10 to the minus 4. So I know my shear stress is 12.6 kPa. My normal stress, I calculate that by using my normal force and dividing that by the corrected area. I calculated my normal force to be 98 newtons, and I divide that by my corrected area. So I get 30.9 kPa as my normal stress. So I would want to plot this on my graph down here. So you'll see with this graph here, I've labeled it as shear stress in kPa versus normal stress in kPa. So it's always important that you label the axes of your graph and provide units, and you will be marked on that on a test, providing the correct labels for your axes and including the units. So you'll see here I have 30.9 and 12.6, and so this is my first data point. I've gone through and I've done the calculations for the other two tests as well, so test 2 and test 3. So, oh shoot, thanks, Brett. I'll start after this. Sometimes you just forget. Okay, so I've gone through and I've done the calculations for the other two data points. And so those two data points, I've provided the answers in PowerPoint presentation, and it's on slide 18. So you can take a look at those. So you'll see that your normal stress associated with test 2 was about 59.7, and your shear stress was 18.9. And with your third test, it was 88.9 was your normal stress, and your shear stress was 29.6. So I plotted each of those three data points on my graph. So I know that because this is a shear stress, or sorry, a direct shear test conducted on clay material, that I'm not going through the data point 0, 0. So I know that inherently I'm going to have a cohesion value. So what I'm doing as well is I'm just drawing a line of best fit that goes through these three data points. So again, this was my line of best fit through the three data points, and it intercepted the y-axis here at about 0 and 3 kPa. Again, I do accept a range. So if you told me it was 5 kPa, or if you told me it was, if you told me it was 4 or 5, well, 5 would be a little off, but if you told me it was 4, or if you told me it was 2, you would still be marked correctly for the process. So similarly to with a sand material, to calculate what my friction angle is, I'm just taking the inverse tan of the slope of this line, and I'm just taking any two data points on the line or on my line of best fit to determine what my slope would be. So that's how I would calculate my friction angle for the clay material. And the cohesion for my clay material is similarly to what we discussed in class last week, where the cohesion is represented by where this line of best fit intercepts the shear stress axis. So you'll see my line of best fit intercepts that shear stress axis at about 3 kPa. So this is my cohesion value. So my cohesion value is represented by where that line of best fit intercepts the shear stress axis. So my cohesion value in this case is equal to 3 kPa. Anyone have any questions on sort of the process for doing direct shear tests with clay? On a test, your shear boxes will always be rectangular in shape, even if for a clay material. If I was ever to test you on a clay material, I would still tell you that your shear box was square, or rectangular instead of being circular in shape. No, so how do we plot this during the test? You plot it on graph paper. So for the test that's coming up, you'll need graph paper and you'll need a compass. So it will be your responsibility. I can send out some graph paper to you guys, and you guys can use that during your test if you want, but you would have to print out. I'll show you what a compass is. It's not one for navigation. It's for drawing more circles. So I can send you guys out graph paper if you like, but it would be your responsibility to print it out. What's considered Okay. Oh, there's lots of questions. Okay, I'm going to start at the top. The compass. So protractors, Kelly, don't work that well because your radius of your circle always changes. So I'll show you guys what a compass is when we get into drawing more circles. For those of you who don't have a compass, you can buy them at the dollar store for $2. That's where I bought mine from. Good cohesion value for clay. Well, Conrad, it typically varies, but we see anywhere between about 2 and 8 kPa for the lacustrine clays in the Winnipeg area. Generally in the 2 to 5 range if they're at their residual values. Our standard, quote unquote, shear strength values that we use for clay material along riverbanks is 2 and 10. So a cohesion value of 2 and a friction angle of 10. At our post-peak values is what we use if we're offset from the river, and we'll use a cohesion value of 5 and a friction angle of 14. I've seen friction angles go as high as 20 if your material is more alluvial in nature, with a slightly increased cohesion value as well, around also the 5 kPa range. Our lacustrine clays in the Red River Valley aren't very strong. Yes, so correct, Pavel. So if you're in sand, your trend line or your line of best fit always goes through 0, 0. So you start at 0, 0 and draw your line of best fit with your 3 data points. If you're in clay, you never go through 0, 0, and your trend line just becomes your line of best fit with the 3 data points that you have on your graph. Okay. So if someone, Conrad, can you elaborate on that? If someone requested a cohesion value. It depends where you are, I guess. If you're along a riverbank, you're probably in the 2 range. If you're offset from the river, you're probably in the 5 range. And that would be the lacustrine clays in the Winnipeg area. If you're looking at in alluvial clays, the cohesion value is sometimes higher and your friction angle is sometimes higher. There are good articles that allow you to use your index properties, so your Atterberg limit testing, to determine potentially what your friction angle and your cohesion value would be in alluvial soils. It's by Peters and Lamb. It's in the Canadian Geotechnical Journal. But generally Winnipeg, 2 and 10. So cohesion of 2, friction angle of 10 along rivers, and a cohesion value of 5 if you're not along a riverbank. So Suraj. Yes, so these values are used in slope stability studies. So yes, so we do direct shear testing for slope stabilization studies. You can request triaxial testing, but generally we just request direct shear because they're cheaper. Direct shear tests are, say, $500 a data point, where triaxial testing is $1,500 a data point. Okay, you guys are probably need a break, so why don't we come back at 10:20 and I will switch gears and we'll go into triaxial testing and we'll have a brief conversation on triaxial testing and more circles, and then we'll get into UU testing and CU testing. So we'll come back at 10:20 and we'll start again. Okay. Everyone back?
Elena,
Yes.
why were you saying you couldn't use a protractor?
Because your radius of your circle changes, depending on. If you can get it to work with the protractor, like if you have one that's able to sort of change radiuses or whatever, then it would work just fine.
Oh, okay.
For students who have iPads or would prefer to graph in Excel or other electronic means, I have no issue with that. Like, in my opinion, that's the beauty of online learning. If you don't want to do it by hand and you program something in Excel or on your iPad or whatever, I'm okay with that. If people prefer to use a compass, like this is a compass. I don't know if you guys can see it. It cost me $2 at the dollar store. They come in all those geometry sets. So for anyone who has kids and they do geometry in junior high or whatever, they come in all those geometry sets. Where you just add a little pencil to it. Mine comes with a pencil lead already in it, so that's why I bought the $2 version. So I didn't, and then it has a tip or a point on one end, and that's what you put on your paper. So, but however people want to plot circles, I'm okay with, as long as it works. So Kelly, if it works with the protractor, great, just use that. Okay, we're going to talk about triaxial testing now. So triaxial testing, oh, do they? Yeah, that's what mine is. Mine's a Statler from the dollar store. It was $2. So triaxial testing is another way in which we can determine shear strength parameters of clay material. So triaxial testing is very similar, or it's similar to unconfined compressive strength testing, where you need a material that has cohesion that can stand vertically unsupported. The similarity between unconfined compressive strength testing and triaxial testing is that an axial stress or an axial load is applied to specimens using both testing methodologies. The difference is, in a triaxial test, your specimen is confined in a triaxial chamber. And within that triaxial chamber, you have a confining pressure or stress that's applied to the sides of your specimen. So if this was my soil specimen, I have a confining pressure that's applied to the sides of my specimen, and it's either applied by water or by air. Whereas with an unconfined compressive strength test, your specimen is open to the atmosphere. So there are two different ways to determine shear strength parameters. The benefit of triaxial testing is you can get long-term shear strength parameters, whereas with unconfined compressive strength testing, you can only get short-term shear strength parameters. More circles. So you plot your data for triaxial testing on something called a Moore circle. So Moore circles, you need a protractor, or sorry, a compass, which I showed you, to plot them. But a Moore circle is used because you can calculate your shear stress and normal stress for every possible angle from 0 to 90 degrees on an imaginary plane and plot this on a diagram. So imagine if I had an angle of 0 degrees. So this is my angle. If I was to apply a normal force to it, like this, that normal force is my axial stress that's being applied. So at that angle of 0, I have an axial stress value, but I don't have any shear stress value. So I just have a normal force that's being applied. Similarly, if I was at 90 degrees, I would have a confining pressure or that's being applied to the specimen, which is also a normal force because it's acting perpendicular to the specimen. Moore circles are unique little beings. The way that you use Moore circles or you plot data on Moore circles is if you plot an angle by multiplying it by 2. So say, for example, if I had an angle of 90 degrees, the way it plots on a Moore circle is I have to multiply that 90 by 2, and it plots at an angle of 180 degrees. So if you see this data point right here, this data point right here represents an angle of 0 degrees, and this data point right here represents an angle of 90 degrees, because I have to multiply the 90 by 2, and it plots at a 180 degree angle. So that's what this schematic right here is just illustrating to you, that you can plot any shear or normal stress on a plane at any angle, and that angle is theta, and it's just an imaginary plane. So it doesn't necessarily represent your failure plane. It's just any imaginary or any plane that exists within your soil surface. And it can be defined by an angle theta by a point on your Moore circle. So say, for example, I wanted to look at an angle theta of 30 degrees from the horizontal. So say, for example, this represented an angle of 30 degrees. This does not write well. So my angle theta in here is 30 degrees. How it would plot on the Mohr circle is it would plot at an angle of 60 degrees. And that's all I really want you to sort of understand from these couple slides. So say for an example on a test, because sometimes you guys like to ask me about tests, I may say to you that you have an angle of 30 degrees. What angle would this plot as on your Mohr circle? So you would tell me it would plot as an angle of 60 degrees on your Mohr circle. Or if I said to you, we have a shear normal stress acting at a point on the Mohr circle, it plotted on your Mohr circle as 60 degrees, what would be your angle theta? You would tell me that your angle theta would be 30 degrees. Okay, so principal stresses. So a solid object can experience different stresses in different directions. So your major principal stress, or your sigma 1 value, is the largest stress that's on an object. So your major principal stress, your axial stress acting is sort of in the downwards direction, is your largest stress, and it's defined as sigma 1. Your minor principal stress is the smallest stress that's acting on an object, and it always occurs at 90 degrees to sigma 1. So it would occur at 90 degrees, so it plots as 180 degrees. So it also plots on your normal stress axis, but it plots at 180 degrees from your major principal stress. When you have a normal stress, and when your normal stress is a principal stress, your shear stress always equals to 0. So if we go back to these plots here, this is shear stress versus normal stress. Your sigma 1 value, it plots right here where you have a shear stress of 0, and your sigma 3 plots at an angle of 90 degrees from it, or 180 on the Mohr circle, and it also has a shear stress of 0. This is just an illustration of your major and minor principal stresses as well. I kind of condensed the slides for this presentation significantly. So my expectation is you still go through and you'll read the theory that was presented on the slides. I just didn't want to go over it in class because I think you can read it, and our time is quite limited together. So drawing a Mohr circle, it's really a graphical method of drawing a stress state of an object. So when you're drawing a Mohr circle, you would generate an X and Y axis. On your Y axis is your shear stress, so your tau value, and on your X axis is your normal stress value. So the important difference between Mohr circles, drawing a Mohr circle, and doing your plots for direct shear testing is your plots on direct shear testing don't have to have the same scale on your X and Y axes. You can just calculate the slope of your line and it's fine, and you don't have to have the same scale. When you're doing Mohr circle drawings, both your X and Y axes have to have the same scale, or the answers that you determine will be incorrect. So that's a very important point, that both your X and Y axes have to be drawn to the same scale. So on your X axis, if you have an increment of 20 per line or per space on your graph paper, then on your Y axis, each of the spaces on your graph paper have to be represented by an increment of 20. The maximum and minimum principal stresses are plotted on your horizontal axis, so on your X axis, with sigma 1 being your largest stress value and sigma 3 being your smallest. You can determine the center of your circle by taking the average of your sigma 1 and your sigma 3 values. And the best way to plot your Mohr circle is you'll see you put the, there's a tip of a compass or a pointy part of a compass. You put it in the center of your Mohr circle, and then you extend your compass out so that the pencil part of your compass intercepts sigma 1 or sigma 3. And I'll show you how to do that when we go over an example problem. The radius of your Mohr circle is also equal to sigma 1 minus sigma 3 divided by 2. So that's what's represented by the radius of your circle. Maximum shear stress for a Mohr circle is always represented at the top of your circle. So the top of your circle right here is always your maximum shear stress. Your maximum shear stress value is always equal to the radius of your circle, because you'll see here, this is the radius of your circle. So your maximum shear stress is always equal to the radius of your circle. When we're doing triaxial test, sigma 1 is represented by your axial stress at failure, and sigma 3 is equal to your confining stress. And I'll talk a bit more about confining stresses in a few slides. So here's a few notes on solving problems with Mohr circles. Use graph paper. Again, as I mentioned, if you prefer to graph in Excel, or you have an iPad and it does graphs for you, or OneNote, I can graph in OneNote. Please feel free to do that. You can do that on a test as well, or you can simply use graph paper. I'll email some out to the class, or you may have your own graph paper. Make sure your scales are the same. Make sure your X and Y scales are exactly the same. So you'll see here on this example, each of the different spaces represent 50 on both the X and the Y axis. And my last tip is use a compass or some sort of means. No, it is not. Triaxial stuff isn't on your quiz this afternoon. I'm not going to give you a quiz on the triaxial stuff. You'll just have to know it for the test next week. Use a compass, because if you're going to freehand it, it's not going to work very well, and you'll frustrate yourself and you'll frustrate me. So use a compass. We talked about notable points already on your Mohr circle, so I'm not going to dwell on that. Mohr circles are used in exactly the same way as your direct shear test data points. You're drawing a Mohr Coulomb failure envelope, and from that Mohr Coulomb failure envelope, you're determining your shear strength parameters. And you determine it in exactly the same way as you determine them for a direct shear test. You can determine what your cohesion value is, because your cohesion value is simply represented as the distance between 0, 0, and where your line of best fit intercepts the shear stress axis. So this is equal to your cohesion value. And the slope of your Mohr Coulomb failure envelope is, or the arctan of it, is equal to your friction angle. You'll note with your Mohr circles, your line of best fit should never be going through the top of your Mohr circle unless your specimen is unsaturated, or sorry, saturated, and I'll get into that. Your line of best fit typically is tangent to the point of maximum curvature of your Mohr circle. So that's typically how you draw your Mohr Coulomb failure envelope if the material is unsaturated for UU, or if you're doing a CU test. And this is just sort of what I just discussed on the previous slide. So I know this was an extremely quick Coles Notes version. There's a lot more on the PowerPoint presentation I gave to you guys on Learn. So make sure you read through that thoroughly. But before I move on to UU testing and go through some example problems, anyone have any questions on Mohr circles before we move on? I'm sure this is new for everybody.
So the whole point of drawing that line is to try to find the angle of the failure.
Correct. It's to determine your angle of failure so you can determine your shear strength parameters. Correct. It's just another tool in your toolbox to determine shear strength parameters.
Because you were drawing, when you draw the half circle, I'm like, okay, are we looking from the top?
You only look for above 0, 0. So anything that's greater than 0. You don't worry about anything that's below 0. Like any negative numbers, we don't worry about. You will need some practice. There are multiple example problems, but it will take a bit of practice with drawing the circles and the lines. Again, there is leeway because again, it's data analysis and interpretation. So I'm looking for the process more so than what your actual, like, were you bang on with your answer? So I have leeway, cohesion, and with friction angle, or I have a range of values that I accept. But you guys will get good at it. I have full confidence. Okay, so we're going to now talk about UU testing. You do need to be able to draw more circles for UU testing. So UU triaxial testing stands for unconsolidated undrained triaxial testing. So what I mean by this is it's another tool in your toolkit to be able to determine your short-term shear strength parameters. So you're able to find your cohesion and your angle of internal friction by using by conducting 3 or more tests at various confining pressures. Okay, so as we talked about, triaxial tests are similar to unconfined compressive strength tests, and UU is an example of a triaxial test. With a UU test, we're applying a confining pressure in a triaxial cell, as I discussed previously, to the sides of the specimen, and that confining pressure in a UU test is applied by air. So there's different confining pressures that are applied, depends on what test you're conducting, because we need a minimum of 3 tests. So in our lab, we usually use 10, 20, and 30 PSI as our confining pressures. So one group would conduct a test with a 10 PSI confining pressure, another group would conduct a test with a 20 PSI confining pressure, and another group would conduct a test with a 30 PSI confining pressure. We try to have very similar specimens that each group is conducting the test on. So we'll collect, so we'll have Shelby tube samples, and we'll divide those specimens or that sample into 3, so that each group has a representative sample that they're testing. You measure your axial force that's applied to the specimen, similar as what you would do in an unconfined test. And we also measure axial compression. So how much is that specimen decreasing in height? Exactly the same as what we would do in an unconfined test. Again, like an unconfined test, we have a constant rate of compression. So we use 1% of the specimen length, same as what we do in an unconfined test. So why is this triaxial test called unconsolidated and undrained? Well, the reason why it's called unconsolidated and undrained is you prepare your specimen, you put the membrane around it, you put it in your triaxial cell, you apply your confining pressure, and you automatically or immediately begin shearing. So you don't allow any drainage of water from the specimen, and we don't consolidate the specimen before we begin the shearing process. So we prepare the specimen, put it in the triaxial cell, and then we begin testing immediately. We're not measuring any pore water pressure, and we don't have the ability for any excess pore water pressure to dissipate or drain because we've closed the drainage ports. Soil fails in less than 20 minutes when we're generally conducting a UU test. So it's a very quick test, similar to unconfined, and it gives us an indication of our undrained shear strength parameters or our short-term shear strength parameters. I'm not going to spend a lot of time on this. Sample prep is pretty much the same as an unconfined test. We have the same L to D ratio. You'll note the diameter is a little bit smaller when you're running a triaxial test compared to an unconfined. You can run a UU test on both saturated or unsaturated specimens. And again, it has to be a clay material because it has to stand vertically unsupported in the triaxial chamber. Okay, there's 2 possible outcomes associated with conducting UU tests. So you can conduct UU tests on either unsaturated material or saturated material. So unsaturated material is anything I would constitute any specimen that has a degree of saturation of less than 95%, I would consider unsaturated. So you'll notice with unsaturated specimens, your soil density increases as you have a higher or a larger confining pressure. So you'll notice here, I did 3 plots, and you'll notice that as my confining pressure or as my sigma 3 value increases in value, also so does the radius of my circle. And my sigma 1 value is also larger as well. So what this means is that as I apply a larger confining pressure, my strength is also increasing because the radius of my Mohr circle is increasing. So this is what transpires when you have an unsaturated specimen. Meanwhile, if you have a saturated specimen, what this means is your degree of saturation is generally greater than 95%. All your specimens have Mohr circles that have approximately the same radius. So you'll see here that the radiuses of the circles that I presented aren't increasing. So all the radiuses are approximately the same. So if this is the case, you're calculating or determining the undrained shear strength of your specimen. So your undrained shear strength would be your CU value. And because you're just plotting a horizontal line, that means that your specimen doesn't have a friction angle. So you're just calculating the undrained shear strength of it. Whereas if you note with this specimen over here, when the material is unsaturated, you're calculating both your friction angle, so from the slope of this line, and you can also calculate your cohesion, because you determine where your line of best fit intercepts your shear stress axis to determine your cohesion value. Yes, and then here, your undrained shear strength value, it represents your short-term stability scenario. So what I mean by this is if I was constructing a large earth embankment and I constructed, say, a meter of this earth embankment very, very quickly, and I didn't allow time for any of that excess pore water pressure in my foundation area to dissipate from adding that additional weight to the foundation area. That's what I mean by short-term loading scenario or short-term stability. Over time, as that excess pore water pressure has time to dissipate and the pore water pressure is back to what it was prior to the load being added to it, that would represent our long-term stability or our long-term shear strength parameters.
Well, once the water starts draining and moving away, wouldn't that cause settlement?
Yes, it does. It does, 100%, Tim. Yes, and that's module 10. So we get into that after this. Yes, 100%. It does start to cause. It does cause settlement, but it doesn't impact your shear strength parameters so much. It just causes settlement in your foundation area. So over time, generally, your shear strength parameters will increase in value as the excess pore water pressure starts to drain away. Generally, your soil is weaker instantaneously or immediately after you apply the load. So the correlation between UU and unconfined compressive strength testing is shown here. You can plot your unconfined compressive strength data on your UU test data, and you'll see that the undrained shear strength value that you determined or calculated from your unconfined compressive strength test matches with your UU test data. And so you can plot that here. So that red circle represents your unconfined compressive strength data. So if you're plotting your unconfined compressive strength data, your confining pressure is equal to 0, and your sigma 1 value is simply equal to your unconfined compressive strength. And you can plot that as a Mohr circle to see the comparison to UU test data. Okay, I'm going to pause there, and I'm going to give an opportunity for you guys to ask questions. I don't know if anyone started this material. Has anyone started working on triaxial tests? Yes, okay. Do you have any questions, Kelly?
No, I'm getting it so far.
You're getting it, okay. I am going to go over 2 example problems. I'm going to go over example problem 7.2. Well, that will be the first one I'll go over. Okay, so example problem 7.2, using the failure data from a UU test, determine the cohesion and angle of internal friction. So, and in parentheses or brackets, it says the specimens were very nearly saturated. So what does that say to you guys? If the specimens were very nearly saturated? What do you anticipate your Moore circle plots to look like? Correct. No friction angle. So the radius of your Moore circles should be approximately equal. So there would be no friction angle, and you're just calculating an undrained shear strength. So if you'll see with the data here, your confining stresses are given to you, and they'll be given to you on any test that you write. So you see there's 69, 138, and 207 kPa, and that represents 10, 20, and 30 psi, what I was talking about, the different confining pressures that we use in the lab. And you'll see from this plot over here, you're also able to determine what your axial stress is at failure, because your axial stress at failure is represented by your maximum axial stress value. So you'll see for 69 kPa, your maximum axial stress is about 218 kPa. At 138, it's about 297 kPa. And at 207 kPa, it's about 373 kPa. So on a test, it would be fair game for me to give you a plot and ask you to determine, you would have to determine what your axial stress is at failure and then go through the exercise and plot your Moore circles. So if we look at this here, again, I like to draw, or I like to make little tables because I find it easier to process the data. Similarly to direct shears, I make data tables for triaxial tests. So you'll see here, I have one column labeled sigma 3, one column labeled sigma 1f, and then I have something called center and radius. So center and radius just represent what is the center of each circle, and radius represents what is the radius of each circle. And I should have 3 circles on my plot because I have 3 data sets from 3 different tests that were conducted. So you'll see here, my confining stress for test 1 was 69 kPa, and my axial stress at failure was 218. So the center of my circle, do you guys remember how we determine what the center of our circles are?
Half times 0.1 plus 0.3.
Correct. So it's just the average of sigma 3 and sigma 1 is the center of your circle. And then the radius of the circle, do you guys remember what the radius is?
Same thing, just subtracted.
Correct, exactly, 100%, perfect. So you can determine what the radius of each of your circles are. So I just went through and I do the exact same calculations for my second set of data. So if this was data set 1, 2, and 3, this would represent data set 1, 2, and 3. So I've gone through and I've calculated what the center of each circle would be and what the radius of each circle would be for each of my 3 different tests. I'm going to move this up a bit. So let's look at our first data set. I know the center of my circle is 143.5 kPa, or so the center of my circle is 140. So each of my squares represents 10. So here. And then my sigma 1f value is 218 kPa. So that represents this point here. So I don't know if you guys can see this, but I have the sharp point of my compass at 143.5, and then I have my pencil part of my compass at 218. So I just draw my circle like this so that it represents the first data set. And I know that my Moore circle should also intercept my sigma 3 value at 69 kPa. So I know that this right here represents 69 kPa, and this right here represents 218. Sorry, right here, and then right here. You'll see here, if I was to draw my circle, it looks like this. So that's my first Mohr circle. My second Mohr circle would be the same. I would put the pointy part of my compass at 217.5. So approximately about right here. And then sigma 1F is about 297. So I'd put my pencil, so the sharp points at the center, the point, my pencil is at sigma 1F, which is 297. And I just draw my circle so that it intercepts my sigma 1 and sigma 3 along the x-axis. So that's how I draw my Mohr circles for each of the different data sets. So I go through and I draw it for data set number 1, data set number 2, and data set number 3. So you'll see here that I have 3 Mohr circles. So this would be data set 1, this would be data set 2, and this circle would represent data set 3. And if you look at your radiuses here, they're all approximately the same. So you know that this represents a saturated specimen. So there's 2 ways in which you can determine your undrained shear strength parameters. You can either determine it from using your Mohr circles and showing me on the plot that you took an average value and you drew your line of best fit along the top of each of these different Mohr circles, and that your line of best fit would give you an undrained shear strength value of about 80 kPa. So this would be about 80 kPa. You can also just average your radius values, and if you average your radius value, you calculate about 79 kPa. So you could say to me your average undrained shear strength is 80 kPa, or your average undrained shear strength value is 79 kPa. And again, we have a range, so both would be marked correct.
Elena?
Yes.
Are those 2 radiuses correct for 2 and 3?
I will double check them.
I don't think they were multiplied by half.
Okay. Yeah, I got 79.5. So 297 minus 138. And 83. So 297 minus 138 times 0.5. I still get 79.5.
Oh, okay.
Do you get that, Kelly?
I must have screwed some up. I'll just double check.
Okay. Well, we can go through it after class as well if you like. So you'll notice here with your Mohr circle plot, you have shear stress on the y-axis and normal stress on the x-axis. I've provided the units of kPa and kPa, and you'll notice that each of my squares represent the same increment. So with the dark line here, each of these dark lines represents 100 kPa on both the x and y axis. So that's why we were able to draw the Mohr circles accurately. So this is how you would go through and do the data analysis and interpretation for a UU test with this data that was given for a saturated specimen. That being said, on a test, I'm not going to tell you if your specimen is saturated or unsaturated. Yeah. You will have to determine that from the shapes of your Mohr circles. So if your Mohr circles are approximately the same radius and the same size, you know your specimen's saturated. If your Mohr circles are increasing in diameter or radius, then you know you have an unsaturated specimen. I'm going to pause. I don't know how many of you have started track field tests, but I'm going to pause for questions in case anyone has any. Well, you would state that your friction angle, Fabian, is equal to 0, but you would state that you have a CU value is equal to 80. So your CU value is equal to 80 kPa. because that represents your undrained shear strength value. And you would say phi u is equal to 0 degrees. So good point. On each of the triaxial tests that you're doing your analysis on, please state what your friction angle would be and what your cohesion value would be, because those are the two shear strength parameters that we're looking for. Okay, the second half of this question asks you to plot the Mohr circle for an unconfined compression test having a QU value of 154. So we kind of went over that quickly. So here, this would represent your sigma 3, which is equal to 0. So you would have a sigma 3 value here. Your sigma 1 F value would be equal to 154 kPa. So that would be equal to 154. So you would determine what the center of your circle would be. So it would simply be 0 plus 154 divided by 2. So what would that be? 77? 77. So you would take your center of your circle here, and you would draw your Mohr circle. Let's see. I'm going to draw my Mohr circle, have an intercept of 0. And you can see that the undrained shear strength value from my unconfined compressive strength test matches well with the undrained shear strength parameters calculated from my UU test. Okay. Before I move on to an example with a with an unsaturated specimen, does anyone have any questions? And then you guys can have a break.
How much more were you hoping to cover today?
Just CU tests after this. I'm open to suggestions. If you guys would prefer like a longer break after I finish UUs, then I can go over it this afternoon, or if you want me to talk about it next week, that's fine. But CU test will be on your test next week. I'm open to suggestions, whatever works best for you guys. Yeah, not the afternoon. Yeah, Friday afternoons usually aren't the best. Anyone have any opinions? I'd like to finish off UUs, and then I'm open to suggestions for CU. If you guys would prefer to just work on CU on your own, and I can upload videos for some of the solutions, I'm okay with that as well. Okay, well, I want to finish off UU. Okay, well, let's finish off UU. And I'm willing to do both. So those who want to stick around can stick around. And then those who would prefer, I can lecture next Wednesday as well on UU tests. Okay, so example problem 7.3 is to determine the cohesion and angle of internal friction from the data below. So this would be example of data from a UU test. And we've done actually 4 separate tests. So you have 4 different confining pressures. And so you have a confining pressure of 69, 104, 138, and 173. And so from the plots here, I'm able to go through and pick off my maximum axial stress value. So here it's around 220, here it's around 285-ish, 325, and 373. So my maximum axial stress values represent my sigma 1 F values. And my confining pressures for each test represent my sigma 3 values. So you'll see here, I have my sigma 3 values associated with each of the different tests. So I have 4 tests, 1, 2, 3, 4. And my sigma 1 F values are 220, 285, 325, and 373. And I got those, as I showed, from doing interpretation of this axial stress versus axial strain plot or graph. So once I have my sigma 3s and my sigma 1 values, I can determine the center of my circle, and I can determine the radius of my circle. I'm not going to go through the calculation associated with each of those, but you know the formulas to use. Again, I've made a plot of shear stress versus normal stress in units of kPa, and both my x and y axes have the same scale. So each dark line represents 100 kPa. So I've gone through and I've plotted each of my different Mohr circles for each of my 4 different tests. And so you'll see with these Mohr circles, the radius of my circle is increasing as my sigma 3 value is increasing. So the radius of the circle is getting larger as my confining stress is getting larger. So you know if that is the scenario that the specimen would be considered unsaturated, and if the specimen's unsaturated, you should have both a cohesion value and a friction value, or sorry, a friction angle value. So I've drawn my 4 Mohr circles, and I'm now going to draw my failure envelope, which just represents my line of best fit for each of these 4 Mohr circles. So this was approximately my line of best fit that intersected as best as I could my point of maximum curvature of each of the 4 different Mohr circles. It really is just a line of best fit. So again, there's leeway within your KP or within your cohesion and friction angle values. So I'm again looking for process more so than a bang on value for cohesion and friction angle. I have a range of values that I accept. So you can determine your friction angle by calculating the slope of your line and taking the inverse tan of it. And you can determine your cohesion by determining where your line of best fit intercepts your shear stress axis. So your line of best fit intercepts your shear stress axis at a value of 50 kPa. So that would represent your cohesion value. So that's how you would determine your shear strength parameters from this UU test data. So it looks something like that. And again, it would be fair game for me to give you a plot of axial stress versus axial strain, and I would provide you with the confining pressures. Yeah, you can use Excel. I have no issue with that. And you would have to determine from these graphs what your maximum axial stress value was at failure. I'm okay with that. So that would be fair game for a test. Okay, let's pause, and I'm available to answer questions on UU. I'll keep going on CU after a 10-minute break for those who are interested, and then I'll arrange something for next week as well, where I'll go over CU with those whose brains are fried after a tough week. Anyone have any questions on the UU test?
So your axial stress, you take that from the apex of the curve, or it starts going down?
Yeah, it's the maximum point on the curve.
Okay,
Yeah,
thank you.
it's the apex. Yeah, exactly. Okay, well, let's pause for a 10-minute break. So we'll come back at 11:15 for those who are interested in staying. For those who aren't, I will have a discussion on CU tests later next week that you can join in if you so choose. So let's take a 10-minute break, and we'll come or reconvene at 11:15. And then I'll release your UC, your unconfined compressive strength quiz results at the end of the CU test lecture. So Pavel, why do you want to know about the retaining wall design?
Well, I was just looking at all those review assignments, and when I looked at that retaining wall design, I was like, "Whoa, that's a lot of calculations." And I thought it's just
No, you guys will be good with that. That unit, most people do really well on.
okay.
This is the hardest. I find these units, so what test number 1 will be on, is what students struggle with the most because it's open to interpretation and data analysis. Moving forward after that, the material I find the students, because it's not, so I won't say subjective, but open to interpretation and analysis, it's, much more calculation based. I find students excel at that content a little bit more.
All right. Well, I personally, I haven't studied this particular section, so I'm looking as you just go with it. I really don't understand what's going on. Like, barely, I mean, I keep, but it's not that, I will need to read it again for sure.
Yeah, and I'm open to meeting with students next week, and we can have conversations on it. Does anyone want me to make videos? Like a couple videos? Kelly? What do you think?
Oh, it doesn't matter. I'm following along.
Okay. Mitch, what units do you want a couple videos for? I'm not going to make videos for every example problem because that takes hours and hours and hours. But I'm willing to do representative problems. So Mitch, is there a unit you want me to focus on? One from each? 7, 8. Yes, I'm going over that one today. So I can make a video of it as well. Are you guys finding it beneficial to go over the example problems, or do you want me to go over less theory, more theory?
100%. It's very valuable. Yeah, it's good.
Do you want me to go over less theory, or are you guys finding I'm going over too much theory?
I personally can read the theory myself, but as you did previously, you kind of extracted the key elements from your full complete presentation. So some theory, but I would say 2/3 of practice would fit best, would fit my needs the best.
Okay. I'm open to suggestions. However, I can best serve you guys. Because you guys said, in hydrology, he lectured for 8 hours, right?
Yes.
I can't imagine lecturing in this for 8 hours.
He only did it for a couple of classes and then
Oh, okay.
kind of gave up.
Okay. What did Mike Robb do?
He did 2-hour classes, and then later on he just posted a bunch of videos when it came out to the heavy course load stuff like the LDS design and the water main and stuff.
Oh, okay.
Actually, Mike used a couple of his videos that he made even back from last year.
Oh, okay. Yeah, I'll make you guys some videos. of example problems from UU or CU. Okay, well, let's get going so you guys can have lunch and enjoy your afternoon. Okay, so consolidated undrained triaxial test is another type of triaxial test that we use. The difference, the reason why we do CU tests compared to UU tests is we want to determine what our long-term shear strength parameters are. So with a CU test, we can determine both what our effective cohesion value is and what our effective friction angle is. And what I mean by that is those are our long-term shear strength values. The difference between CU and UU tests is CU tests are, always have soil that's saturated. So what we do in a CU test is we saturate and consolidate the soil within the triaxial chamber for a week. So remember or recall with the UU test, I said you just put your specimen in the triaxial cell, you apply your confining pressure with air, and then you shear instantaneously. With a CU test, you put your specimen in the triaxial chamber, you apply your confining pressure, but it's applied with water this time, and you consolidate and you saturate and you consolidate your specimen concurrently, and that process takes about a week. So you leave the specimen in that chamber for a week. You open your drainage ports in your triaxial cell so that your excess pore water pressure has time to drain as your specimen is consolidating. Then you close the drainage ports a week later, and then you shear your specimen. So you conduct your testing for your CU test. Your shearing rate is quite low again. So you're shearing at 1% of the sample length per hour. So usually we're 1% of the sample length per minute, but now we're 1% of the sample length per hour. So it's a slower shearing process. It usually takes us about 4 to 5 hours to shear the specimen. During that shearing process, we're measuring pore water pressure. So with a UU test, we're not measuring pore water pressure, even though excess pore water pressure is being generated. Whereas with a CU test, we're measuring that excess pore water pressure that's being generated. And we have those values that we can use to determine our effective shear strength parameters. This is the data, or this is how you would plot your data from a CU test. You'll see it's similar to a UU test where you plot axial stress versus axial strain. With a CU test, you also plot your pore water pressure versus axial strain. So when you're doing your CU test, you would measure your axial stress, say at every 1 minute increments, or you'd measure axial force and you convert it to an axial stress. But you also measure your pore water pressure at those 1 minute increments. So you'll see here that you have representative pore water pressure data over the duration of the test. The thing to note with determining your pore water pressure at failure, you can determine your axial stress at failure because it's the apex of that curve on the graph. Your pore water pressure at failure does not represent the apex of your pore water pressure graph. Your pore water pressure at failure corresponds to the pore water pressure for your axial stress at failure. So you'll see that this data point right here represents your axial stress at failure. So if that represents your axial stress at failure, your pore water pressure at failure is determined by drawing this vertical line down to this point right here, and this data point right here represents your pore water pressure at failure. So that's a very important point to note with the CU test, that your pore water pressure at failure may not be your maximum pore water pressure value that's recorded. With a CU test, you're determining your effective confining pressure and your effective axial stress at failure. So effective, similarly to when we were in Module 4, effective is just simply your total value minus your pore water pressure value. So if our maximum or our axial stress at failure is 275 kPa, that represents our total axial stress. So to determine our effective axial stress, we simply go our total axial stress minus our pore water pressure value. And if we know our pore water pressure value is 148 kPa, our effective axial stress is 127 kPa. And our effective confining pressure is similarly calculated. We know that our total confining pressure is 207 kPa, and we will subtract our pore water pressure to get our effective confining pressure. And this is important because if you look at these plots here, for a CU test, we're plotting our shear stress on the y-axis versus our effective normal stress. So the key difference between a CU test and a UU test is this word effective, because effective indicates that you've taken away or subtracted your pore water pressure from both your confining stress or confining pressure and also from your axial stress. So what you're plotting is slightly different, so your axes should be labeled differently as well. The reason why the term shear stress doesn't have effective in front of it is because shear stress is equal to sigma 1 minus sigma 3. And I'm sorry for the mess. So sigma 1, if we were to calculate effective, sigma 1 would be sigma 1 minus u minus sigma 3 minus u. And this would become this all in brackets, and I'm sorry for the mess. But you'll see here this minus minus becomes a plus u. So the pore water pressures actually balance each other out. So it really is just simply sigma 1 minus sigma 3, which is simply your shear stress. So that's the reason why shear stress doesn't have the word effective in front of it. But normal stress is required to have the word effective in front of it. Don't spend too much time worrying about this because we're not doing the test in person. Generally, we consider our specimen to have failed when it reaches its peak or its maximum axial stress. So don't spend too much time worrying about that. Here again is just another plot of axial stress and pore water pressure versus axial strain. So you'll see from this plot here that our axial stress at failure would be this data point. And if we were to draw a vertical line down, this represents our pore water pressure at failure. So this value right here, which is about 164 kPa. This isn't our maximum pore water pressure value, but this is our pore water pressure value that we use when we're determining our effective axial stress and our effective confining stress. I'm going to pause there to see if anyone has any questions about how you determine pore water pressure or how you calculate effective effective confining pressures or stresses or effective axial stresses. Okay, you guys are all quiet. Okay. So this slide here, yes.
For the last one, how did you do the bottom one?
Yeah, that's obliquity. Don't worry about it. It's just a ratio. So if you see here, this ratio of sigma 1 prime to sigma 3 prime,
yeah,
that's how you plot that. But don't worry about it.
Okay, so just the two top ones.
Yes.
Okay.
Even if we were to do the lab in person, Kelly, we don't plot obliquity. This gets confusing. So this slide here just illustrates the difference between a Moore circle if you were to plot it from a UU test or a CU test. So this Moore circle on the right here was data that was plotted from a UU test. So you'll see here, this was the data. You had sigma 1, which is 100 kPa, and you had sigma 3, which is 30 kPa. Well, imagine if this was data from a CU test. Well, now with a CU test, we have pore water pressure, and our pore water pressure was measured to be 20 kPa. So to determine to plot our Moore circle for the CU test, we have to take our pore water pressure value away from both sigma 1 and sigma 3. So sigma 1 would now become sigma 1 prime because it's an effective value, and it plots at 80 kPa right here. And our sigma 3 would become sigma 3 prime because we're taking away pore water pressure of 20, and it was originally 30, so it plots as 10 kPa. So this plots as our new circle for CU test data. So the interesting thing to note is if you look at the circle center for this test that was conducted in CU and the circle center for this test that was conducted using UU, the difference in the circle centers is simply your pore water pressure value. So the difference in the value for your circle centers in this instance would be 20 kPa, and that's the same value that your pore water pressure is. So the circle centers, they're offset from each other by your pore water pressure value. So when you're doing a CU test, your Mohr circles shift to the left, and they shift to the left by the amount equal to your pore water pressure. You'll notice the radius of the circles don't change. It's simply just the circle center location changes. That's 80 minus 30. No, it's 100. So it's 100 minus 20 gives you 80. Did I say it incorrectly? And then it was 30 minus 20 would give you 10. Oh, sorry, Fabian. I meant this to be the circle center of this circle here. And I guess it sort of plots sort of where the 30 is. I'm sorry. I just meant this to be the circle center of this red circle right there. So that's my bad. I'm sorry. Okay, so shear strength in terms of effective stress. A CU test gives you your effective cohesion value and also your effective friction angle. Whereas with a UU test, it just gives you your cohesion value and your friction value. So effective stress parameters are always identified by this nomenclature or this prime value. So you'll see here C prime and phi prime. So these represent your long-term shear strength parameters. And when you're doing a CU test, when you're identifying your shear strength parameter, make sure you include the C prime and the phi prime, because those are very important, because that enables the user to understand that they're your long-term shear strength parameters. Okay, and the key points here, I think I've drilled this enough. CU tests and CD tests represent your effective shear strength parameters, and your UU test represents your total shear strength, or your total stress parameters. Just an example. This formula right here is the formula that you use to calculate what your shearing angle would be. So if you go through and you do the calculations and you determine that your friction angle is, say, 18 degrees, if you want to determine what your failure angle is, you just go 45 degrees plus 1/2 times 18, and you can determine what your failure angle is from your friction angle. And this is just an example where we calculated the friction angle from a CU test, and from that friction angle, using this formula, we were able to verify the angle of our failure plane, and we were able to measure the angle of our failure plane from our specimen, and they corresponded quite well. Okay. Anyone have any questions before I go over an example problem? I'll make a video of example problem 7.6 of me solving that for you guys. And then I'm going to go over example problem 7.7.
Hey, Elena.
Yes, Sean.
I don't know if I missed it, but can you like what is the difference between the total stress and the effective stress in terms of like real world characteristics?
Okay, real world characteristics. Total stress would be going back to that embankment scenario. If I was to construct an embankment on a foundation area and I put all the load from the embankment there instantaneously, or say I'm doing a foundation for a building and I construct the foundation and I apply the load from that structure instantaneously. So my total stress parameters are what is the strength of my soil when I'm applying that load instantaneously. So my pore water pressure goes up, it hasn't had time to dissipate, and it's pushing those soil particles apart. So my shear strength parameters of my soil are typically lower than what they were before I added the load. Your effective or long-term shear strength parameters are you've applied the load, the pore water pressure has had time to dissipate. So instead of pushing the soil particles apart because there's a bunch of extra pressure in that void space area that's filled with water, that water pressure has gone away. So your soil particles are able to come closer together and they're able to have more contact. So the strength of your soil has gone back to what its pre-construction strength was, and it's increased, the strength has increased compared to when you had applied that load suddenly to the area. Does that make sense?
Makes sense. Thank you.
Okay. I like questions, so please keep asking them. Okay, I'm going to go through this example problem, and then you guys are free to go. So this example problem here is asking you to determine your effective cohesion and effective friction angle from the test data below. So I'm going to go through how we determine what our test data is for each of these different plots. So you'll see here, again, I'm a lady of tables. I quite like tables. I find it an easy way to communicate or portray information. So obviously we have 4 sets of data. So I just labeled them as tests 1, 2, 3, and 4. With each of those tests, we'll have an axial stress at failure and we'll have a pore water pressure at failure. So if we look at this test right here, we'll label this as test number 1. So we'll see here, I'm going to take a look. This top line is my axial stress plot. So I'll take a look here. This looks approximately to be my peak axial stress, which is around 330 kPa. And I'm simply just measuring it off the graph. So I'll say this is my peak value, and I'll just sort of go over to this to the y-axis over there and say, oh, that's about 330 kPa. I'm then going to draw a vertical line down to my pore water pressure line. So this is my pore water pressure line on my graph. And I'll be like, okay, at my peak axial stress, my pore water pressure value is around 162 kPa. And I'm simply just getting that value from reading it off from the y-axis on the plot. So that's how I'm determining what this value is for this data set. I find it easier to go through and determine what your sigma 1 and your sigma 3 values are for each of the different tests. So if we take a look at here, I'll also take a look and go, okay, my confining pressure, my sigma 3 value represents my confining pressure, and it's 242 kPa. So I have my sigma 1 value is 330, my sigma 3 value is 242, and my pore water pressure is 162. So I'm going to go to my second set of data, which is this plot right here. So this represents my second set of data. I'm going to say, okay, axial stress is my top line, and this is about the peak of my graph, and that's at about 510 kPa. Again, I'm just reading it off from the y-axis over here. I know my confining pressure is 345 kPa, so that represents my sigma 3 value. And then I'm going to draw a vertical line down, and I'm going to see where that vertical line intercepts my pore water pressure curve, which is this dashed line right here. So I can see, again, just reading it off the graph, that my line intercepts the pore water pressure curve at about 210 kPa. So that's my second set of data. So I included 210 kPa. So this will be my third set of data. This one's a little bit easier. It has much more of a defined peak. So axial stress at failure will be the top of this curve right here. So if I look at this, it's around 302 to 305 kPa. Again, just reading it off the y-axis over here. So that's my axial stress. My pore water pressure, again, I'm just going to draw a vertical line down to where it intercepts the pore water pressure. And it's around, at this point, it's about 145-ish kPa. Here I wrote 146. And I know my confining pressure is 207 kPa. So my axial stress, sigma 1, is 302. My confining pressure, or sigma 3, is 207. And my pore water pressure is 146 kPa. So I just included that value there, 146 kPa. And similarly, you would go through the same process with plot number 4, and you would determine what your sigma 1 value is, and you would determine what your pore water pressure is. And then always the plots will include your confining pressure. So you're never expected to calculate or determine what your confining pressure is, because they're always provided to you on your plots or on your graph. So I'm going to pause here and see if anyone has any questions on how we determined what our sigma 1 values are, our sigma 3, or our pore water pressure values. No one has any questions? Does it make sense? Yes. Okay.
Yes.
Okay, so now, okay, good. Okay, so now we have our values of sigma 1, sigma 3, and our pore water pressure. These are our total stress values. So now we have to determine what our effective stress values are. So we know we determine effective stress by using our total stress values and minusing pore water pressure. So if we want to determine what our effective axial stress is, we're simply going our total axial stress, which is 330 kPa, and we are going to minus 162 kPa. So if we go 330 minus 162, our effective axial stress is 168 kPa. Similarly, for our effective confining stress or pressure, it's simply 242 kPa, which is our total confining pressure, minus our pore water pressure of 162. So 242 minus 162 is equal to 80 kPa. So our effective confining pressure is 80 kPa. And then I calculated what the center of our circle would be. The center of our circle represents the center of our circle for our effective axial stress and our effective confining pressure. So our center of our circle is sigma 1 prime plus sigma 3 prime divided by 2. So that's what's represented by our center of our Mohr circle. So we have all of this data. We're armed with all of this data, and now our responsibility would be to plot up the data. I don't know how this is. Oh, maybe it would work kind of to do this. Don't know if this is all going to show up. Kinda. Sorry, I'm trying to manipulate the IPvo here a bit. The IPvo can only go so tall. And then it I don't know, about the best I can do. Anyways, okay, we have our data, and now I have to plot the data. So here you'll see on my graph right here, the X and Y scales have to be the same. So each major grid line represents 50 kPa on both my X and Y axis. You'll see my plots are labeled, or sorry, my axes are labeled shear stress in kPa, versus effective normal stress in kPa. So the effective, can I fold the paper? Yeah, I can try to fold the paper. That kind of works. Is that better for you guys? Move my hand out of the way. Okay, there we go. And I'll do this. Okay. IPvo becomes finicky. Okay, so we'll look at our first Mohr circle here. Where did my compass go? Okay, so I know the center of my circle is 124 kPa, so that represents 5, about this data point right here. I know my sigma 3 value is 80, which represents this data point right here, so I can draw my first Mohr circle. So this Mohr circle represents the data from test number 1. Similarly, I could go to test number 2, and I know the center of my circle is 217 kPa. And I know sigma 1 is 300. So I can, sigma 1 prime is 300. So I can move the pencil of my compass out, and I can draw my second Mohr circle. And I go through the same process for test number 3 and 4, and I end up with these 4 Mohr circles. And these Mohr circles, they don't all have the same point of maximum curvature where you can just draw a really nice line of best fit. You kind of have to do some data interpretation and decide how you want to draw your line of best fit. So what I tried to do here was I tried to draw my line of best fit. So it intercepted this Mohr circle at its point of maximum curvature, was a little bit lower for this Mohr circle here, but it was a little bit higher for this one and a little bit higher for this one. So my line of best fit, I just kind of drew like this. My line of best fit intercepted the y-axis at about 5 kPa. And so that would be my effective cohesion value. And my effective friction angle was about 19 degrees when I calculated the slope of the line. So with CU tests, sometimes the Mohr circles don't exactly line up, but just do a line of best fit. Again, I'm looking for process, and there's a range of values that I'll accept for your shear strength parameters. So that's this is the most complicated question I would ever give you on a test, and I can say to you for CU data that I don't even think I would give you the data and ask you to interpret what your maximum axial stress would be on a test. I think for UU it would be fair game, but not for CU. But this is the most complicated question that you would see. But you won't even have a question this complicated on your test. But I just wanted you to be familiar with the process because you do have to know how to plot CU test data. So I'm going to pause and then I'm going to see if anyone has any questions. Okay, let's leave it at that. Did you guys want me to discuss briefly the test for next week? Or do you want me to just send you, like I will send an email as well. Do you want me to talk about it? Okay, I will talk about it. The test next week, it will be at 9 o'clock next Friday, because I'm assuming no one wants to write a test on Friday afternoon. The test will be 3 hours in duration. It will be an enforced time limit. You can't page forward or page back. So how I've set it up is that each module has a page on the test. So say, for unconfined compressive strength test, all the questions associated with unconfined compressive strength test would be on one page of the test. So you don't have to flip back and forth between concepts. The concepts, or each module has all the questions associated with it on one page of the test. I think there's 5 or 6, maybe a few more pages on the test, but you can't go back and forth between the various pages. I will clearly identify to you in my email how many questions are associated with each module on each page and how much each of the questions are worth. So you'll know exactly how much each question is worth before you start the test, and how much each question in each module on each page is worth as well. Anything that requires you to draw a Mohr circle or direct shear test data, I'm asking that you submit that into a Dropbox at the end of the test. That's not included in your 3-hour time limit. You'll have 15 minutes after the test to upload your work into the Dropbox. So again, I'm marking on process more so than I am marking on answers. I just want to see the process. And that's hard to communicate when you're writing a test on Learn. So the test will be on Learn. So that's how you will access it. Prior to starting the test, you have to do an academic integrity quiz, which is simply one question, and you can't access your quiz or your test until you complete that academic integrity test. And it's just simply one question saying, I agree that I will be doing the test on my own. So that's the test. You will need a compass or some other sort of graphing software to do the test. Graph paper, I can email out graph paper to you guys. Do people want me to do that, or? Okay, I can email out graphing paper to you guys. You'll have to print it out then, and then that's how you would submit your work to me. This will be the hardest test of the year. I'm sorry to tell you this, but it is generally the hardest test of the year because there's data analysis and interpretation. After that, it just simply becomes calculation questions for all subsequent units because, yes, it is on modules 1 through 8. So anything associated with modules 1 through 8 is fair game. Obviously, some modules would primarily or solely be theory-based. So if you look at module 1, subsurface investigations, there's no calculation questions associated with it. It will take you most of the 3 hours to write the test. So you can't learn the material as you're writing the test because you won't finish the test. But all modules are represented in the test. Anyone have any questions on the test? And I will summarize all of this in an email for you guys as well. Awesome. So what I've done, Fabian, is there will be multiple choice questions. So Fabian, what I've done is there's a review assignment that I've uploaded onto Learn. So it's calculation based, and there's also theory questions on that. I don't give you the answers to the theory questions because those answers are in the PowerPoint slides. What student groups have done in the past, or what students have done in the past, is divide and conquer. So someone might take 5 or 7 questions of the theory and they work in a group of 4, and then they just swap answers. And that's okay if that's what you guys want to do. But most of the theory questions do come off the PowerPoint, but I have given you in your review assignment very typical theory questions that would be asked on the test. So the PDFs, I'm assuming you mean like the course notes. So no, they're off of the PowerPoint. So if I look, Tammy, theory of the 43 marks, there's 10 marks of theory. Oh, there might be more than 43 marks, but there might be around 10 marks for theory. If I look at this. But I'll send all of that out to you guys in detail, outlining how many questions in each section or from each module and how much each question is worth for each of the different modules. Anyone have any other questions? Someone must have a question. No? Okay. I'll arrange, I will likely be for Wednesday of next week, where we can meet up to go over the review assignment, and I'll give another lecture on CU for those, I guess, who missed it. I'm open to suggestions how I can better, like the lecture style can better suit you guys, what works for you, what doesn't. We can make modifications starting in week 5 if you like. I'm open. So that you guys can learn most effectively. Otherwise, you guys are free to go. Just give me a couple of minutes and I'll open your quizzes for unconfined. Those of you who got 8 out of 8, there will be nothing for you to look at. Those who didn't, there will be. And then I will also open up your direct shear quizzes next week on Wednesday as well. And I'll email out that time to you guys so you can look at them prior to the test next week. So thank you very much for joining me today. And yeah, just give me a couple minutes and I'll open the UCF. Okay, have a good day, everyone.
Elena,
Yes.
you said just open the quiz we just wrote for access to study, right? Not another quiz?
Yeah, so for the unconfined, Kelly, is if you wanted to look at your unconfined because you didn't get 8 out of 8, that will be open for students to see where they made their mistakes.
Oh, okay.
And same with direct shear. I'll open the direct shear next week as well, so students can take a look at the questions that they didn't get correct on the quiz.
Okay. Yeah, thank you.
Yeah, no problem.
Have a good day.
Yeah, you too. Yes, Graham. Okay. The 10-to-1 ratio is for the direct shear apparatus that we use in the lab. So for the direct shear apparatus in the lab, we always multiply the weights that we add to the lever arm by 10 to represent the 10-to-1 ratio. So if I said that we added 8 kilograms of weight to the lever arm, you would multiply the 8 by the 10 to represent the 10-to-1 ratio, and then you would multiply that by gravity. And that's just for the lab testing portion. I won't do the same thing on the test next week. Okay, perfect. Thanks, Graham. Penny or Conrad or Yonel?